So today we're going to talk about Chapter 7, Quantitative Composition of Compounds. And while that title might sound very complicated, quantitative, we're talking quantity, how many, how can we count? And when we're looking at this picture, we can see that this compound, calcium carbonate, has tiny little spheres looking like pearls, and we can measure them out either by weighing or by counting them. So in this video, we're going to talk about sections 7.1 and 7.2. The mole, and we've been mentioning this a couple times this semester, but we're talking about how chemists keep track of compounds and individual molecules of these compounds. We can't say that we need 30 grams of this compound and 25 grams of this compound. In order to make things easier, we use this conversion called the mole. And so what I want you to think about is when you go to the supermarket and when you're buying produce, you're not going to buy 6 apples. You usually weigh out the apples, and you understand that's how it's priced, by price per pound. So if we were looking for the average mass for a piece of fruit, knowing how many we had, we can tell the exact weight. So if we have one orange that has a mass of 186 grams, then 75 oranges have what mass? Easy conversion factor, we're just going to multiply these two, but we want to keep track of our units. So we have 75 oranges multiplied by a conversion factor 186 grams over one orange. That's going to give us 13,950 grams or 13.95 kilograms. And we end up counting atoms very similar to this. So the mole is 1 mole equals 6.022 times 10 to the 23rd objects. This number is named after a scientist who discovered them, Avogadro. So this number is also called Avogadro's number. And so we're going to use this as a way of counting individual molecules. Molecules are so small, using 1 dozen equals 12 objects isn't going to work for molecules because we're going to be talking about hundreds and hundreds of thousands and millions of molecules at once. So the mole is often abbreviated as MOL, so we just drop off the E when you're using your conversion factors. And I want you to think of 1 mole of atoms as being 6.022 times 10 to the 23rd atoms. Here we could be talking about one element. 1 mole of molecules equals 6.022 times 10 to the 23rd molecules. So here we're talking about molecules of a compound. And we could use these relationships as conversion factors. So we can have 1 mole on top, 6.022 times 10 to the 23rd objects on the bottom, or we can flip that. And so think about what types of conversions we can use based upon what units are in the denominators of these conversion factors. So when we talk about molar mass, we're talking about the mass of 1 mole of an element or a compound. And so molar masses are usually expressed to 4 significant figures. And by determining molar mass, we're going to again use the atomic mass that we see on the periodic table. So if we wanted to calculate the mass of calcium fluoride, we would take the atomic mass of calcium off the periodic table and also the atomic mass of 2 fluorine atoms because our formula shows they need to be CaF2. So that would give us 78.08 grams. That means that 1 mole of calcium fluoride is 78.08 grams. So now let's look at some examples. How many moles of lead does 15 grams of lead represent? Easy conversion factor, right? We're going to be going from grams to moles. So here are our 2 conversion factors. And again, this 207.2 grams is taken from the periodic table. So if I ask for 15 grams, we're going to use the conversion factor that has grams on the denominator. Our units will cancel out. It's just simple division. We have 7.24 times 10 to the minus 2 moles of lead. Here, try this one on your own. Pause the video and then check your answer. Okay, so how many moles of mercury does 23 grams of mercury represent? We're going to have our same 2 conversion factors from the periodic table, starting with 23 grams, multiplying it again by the conversion factor with grams on the bottom, gives us 1.15 times 10 to the minus 1 moles. This answer is B. So much like elements, we can also do this for compounds. So the molar mass of a compound is equal to the sum of the molar masses of all the atoms in the molecule. So for H2O, we're taking the molar mass of one oxygen, adding the molar mass of hydrogen, and multiplying it by 2 because we have that subscript 2 in the formula. So the molar mass of water would be 18.02 grams. So let's go through one example. What is the molar mass of aluminum hydroxide, AlOH3? Pause the video now. Try and do this one on your own. Okay, so how would we set this one up? We get the masses from the periodic table. So one aluminum is 26.98 grams. 3 oxygens each are 16 multiplied together. 3 hydrogens are 1.008. We add all those up and consider significant figures, and we get 78 grams. So this answer is also B.